Everything you see, everything you can touch has a property we call mass. It's what gives an object weight here on Earth. Mass is the resistance an object has to being moved, its inertia. A football is easy to kick. A bowling ball is much harder. That difference is mass. For a long time this was just a given, a fundamental property of matter. But in the world of particle physics, where we delve into the building blocks of reality, just because is never a satisfying answer. The equations that so beautifully describe the forces of nature, the standard model of particle physics, worked almost perfectly, but they had a glaring hole. They predicted that all fundamental particles should be massless, zipping around at the speed of light. This is clearly not the case. We exist, we have mass. The universe has structure. So a profound question arose: where does mass come from? The problem was a deep one. The theories describing the weak nuclear force, which governs things like radioactive decay, required the force-carrying particles, the W and Z bosons, to be very heavy indeed. Yet the underlying mathematical symmetry of the theory demanded they be massless. It was a paradox that threatened to bring down our entire understanding of the subatomic world. If these particles had no mass, the weak force would have an infinite range, just like electromagnetism, and the universe would look entirely different. Stars wouldn't shine in the way they do. The elements that make up our bodies wouldn't have formed. The very existence of a stable, complex universe depended on certain particles having mass, and our best theories couldn't explain it. This wasn't just a minor detail, it was a fundamental contradiction at the heart of physics. To solve this, physicists needed a mechanism. They needed a way for particles that should be massless according to the elegant symmetries of the theory to acquire mass in the real world. Think of it like a beautiful, perfectly symmetrical snowflake. The laws of physics governing water molecules are symmetrical, yet when they freeze, they form a unique, less symmetrical crystal. Something had to break the initial perfection of the theory to allow for the untidy, massive reality we observe. The answer, proposed in the 1960s, was radical. It wasn't that the particles themselves had mass intrinsically. Instead, mass was proposed to be an acquired property, something granted to particles by their interaction with an invisible, universe-spanning entity. This new idea suggested that the vacuum of space isn't truly empty. It is filled with a kind of energy field, an invisible presence that permeates every single cubic centimeter of the cosmos. This field had been present since a fraction of a second after the Big Bang. It was this field that would solve the mass problem. It would provide the mechanism to give heft to the building blocks of the universe, transforming a universe of massless, light-speed phantoms into the substantial, structured cosmos we inhabit. The search for this mechanism became one of the great quests of modern science, a journey to understand the very origin of substance. It was a search for what has become known as the Higgs field. Imagine a large crowded party filling a grand hall. The people at the party represent the Higgs field, spread evenly throughout the room. Now, a person who isn't very famous walks in. They can move through the crowd quite easily, with people barely noticing them and making way without much fuss. This is like a particle that doesn't interact strongly with the Higgs field. It encounters very little resistance as it moves through space. As a result, it has very little or no mass. The photon, the particle of light, is just like this. It passes through the Higgs field completely unhindered, which is why it is massless and travels at the ultimate cosmic speed, limit the speed of light. It doesn't pick up any drag from the crowd. Now imagine a very famous celebrity enters the same party. As they try to walk across the room, they are immediately surrounded. A cluster of partygoers forms around them, wanting to talk, take a picture, or just be near them. Their movement is impeded. It's much harder for them to get from one side of the room to the other. They have become heavy. This is precisely how the Higgs mechanism gives mass to other particles. Particles like the W and Z bosons, or the quarks that make up protons and neutrons, interact strongly with the Higgs field. As they move through it, they are constantly interacting, effectively being dragged back by the field. This resistance to movement is what we perceive as mass. The stronger the interaction, the greater the resistance, and the more massive the particle. This concept is truly profound. It means mass is not an inherent property of a particle, but rather a measure of its relationship with the cosmos. It's an environmental effect. A particle's mass is determined by how much it feels the presence of the all-pervading Higgs field. Some particles, like the electron, interact with it only lightly and so have a small mass. Others, like the top quark, the most massive fundamental particle discovered, interact with it incredibly strongly, making them extraordinarily heavy. The Higgs field acts as a sort of cosmic treacle, a substance that fills space and makes it difficult for certain particles to move. It's the very thing that gives substance to the universe. The beauty of this idea is that it solved the mass problem without destroying the underlying symmetry of the equations. The equations themselves could remain perfect and symmetrical, describing a world where all particles are inherently massless. The Higgs field then provides the real-world conditions that break that symmetry and manifest the mass we observe. The laws are pristine, but the state of the universe is not. This process, where the underlying laws are symmetrical but the outcome is not, has a name in physics. It is called spontaneous symmetry breaking, and it is a cornerstone of our understanding of how the complex universe we see today could emerge from a much simpler, more symmetrical beginning. To understand spontaneous symmetry breaking, let's use a simpler analogy. Imagine placing a ball perfectly on the tip of a wine bottle's punt, the dimple at the bottom. The situation is perfectly symmetrical. The ball has an equal chance of falling in any direction around the rim. Gravity pulls it straight down, but the bottle pushes straight up. There is no preferred direction. This is like the early universe, where the fundamental laws were perfectly symmetrical and the particles were massless. The system is in a state of unstable but perfect balance. From this vantage point, all directions look the same. It is a state of pristine yet precarious symmetry. Now, what happens next is inevitable. The slightest nudge, a tiny quantum fluctuation, will cause the ball to roll off the tip. It will fall down into the circular trough of the punt and come to rest at a specific point. The key thing here is that the ball had to choose a direction. The final resting state is no longer symmetrical. There is now a specific chosen direction in which the ball has fallen. The underlying law of gravity is still perfectly symmetrical, pulling downwards, but the outcome, the ball's final position, has broken that symmetry. This is spontaneous symmetry breaking. The universe in its infancy was like the ball at the top. As it cooled after the Big Bang, it fell into a lower energy state. The Higgs field settled into the trough, breaking the initial perfection. This settling of the Higgs field is what turned it on across the universe. Before this moment, just fractions of a second after the Big Bang, the universe was a very different place. It was a searingly hot soup of massless particles, and the perfect symmetry of the physical laws was manifest. But as the universe expanded and cooled, it underwent a phase transition, much like steam condensing into water. The Higgs field acquired a non-zero value everywhere. This was the moment the symmetry was spontaneously broken. The universe chose a direction in the abstract mathematical space of the theory, and in doing so endowed particles like quarks and electrons with mass. The universe as we know it began to take shape. When a field like this exists, it's possible to create an excitation within it, a ripple. Think of the surface of a still pond. The water is the field. If you throw a stone into it, you create a wave, a ripple that travels outwards. This ripple is a localized disturbance of the field. The Higgs boson is exactly this. It is a quantum excitation, a ripple in the Higgs field. Finding the Higgs boson would be the ultimate proof that the field itself is real. Its discovery at the Large Hadron Collider at CERN in 2012 was a monumental achievement. It was like finally seeing the ripple on the pond, confirming that the water was there all along. The discovery of this particle was the final crucial piece of evidence confirming the theory of how mass originates. The Standard Model of particle physics is one of the most successful scientific theories ever conceived. It describes three of the four fundamental forces of nature: electromagnetism, the weak force, and the strong force, and classifies all the known elementary particles. It is a stunning intellectual achievement, a rulebook for the universe at its most fundamental level. For decades, it has been tested with incredible precision, and its predictions have been confirmed time and time again. However, without the Higgs mechanism, the entire structure would collapse. It would be like a magnificent Roman arch built without its central keystone. The pieces would be there, but the entire edifice would be mathematically inconsistent and fall apart. The Higgs mechanism is that keystone. It locks the whole structure of the standard model into place. It explains why the carriers of the weak force, the W and Z bosons, are so heavy, while the carrier of the electromagnetic force, the photon, is massless. This mass difference is critical for explaining why the weak force has such a short range, confined within the atomic nucleus, while electromagnetism has an infinite range, holding atoms together and allowing light to travel across the cosmos. Without the Higgs, we would have no explanation for this fundamental difference between forces. The theory would predict that they should behave similarly, which they clearly do not. The Higgs provides the elegant solution that allows these forces to coexist within one consistent framework. The discovery of the Higgs boson in 2012 was therefore a moment of profound triumph for physics. It was the culmination of a nearly 50-year search involving thousands of scientists and the construction of the most complex machine ever built, the Large Hadron Collider. Finding this particle, with a mass that was predicted but not guaranteed, was the final confirmation of the Standard Model. It meant our understanding of the subatomic world, encapsulated in this beautiful theory, was correct. It was the missing piece of the puzzle, the capstone on a half-century of particle physics research. It transformed the Higgs field from a clever theoretical idea into a tangible, proven feature of our universe. Understanding the origin of mass is not just an academic exercise, it is fundamental to our cosmic story. The Higgs mechanism allowed for complexity to emerge from the simplicity of the early universe. By giving particles mass, it allowed them to clump together under gravity to form galaxies, stars, and planets. It allowed for the rich chemistry that led to life itself. Without mass, there would be no atoms, no us, no one to even ask the question. The Higgs mechanism is therefore not just a detail of a remote theory. It is woven into the fabric of our own existence. It is a deep connection between the vastness of the cosmos and the tiny fundamental particles that are the building blocks of everything.